Hi, I'm Angus. I'm an incoming postdoc, outgoing senior research assistant at Princeton, supervised by Jim Pavarsky, who's here somewhere in the ether. And my work at Princeton has been predominantly on the awkward array project, although of course any project in scikit-HEP tends to spill out and touch multiple different projects in the ecosystem. And I think I'd sort of describe my interests as being holistic software development, which is a word I've definitely just made up. It probably already exists, but this is the meaning I'm applying to it. So a bit of everything from CI/CD documentation. And so because of that, there's no one thing that I thought would be a good talk for my talk today. But what I have been doing more recently is interacting with building applications for the web. And in particular, thinking about some of the challenges that can bring for high energy physics and where it might be appropriate for us to be considering this. So my talk is on HEP in the browser using JupyterLite and Emscripten Forge. And if my slides work, try that again. There we go. So I thought I'd start with a summary, sort of a history, if you like, of running Python in the browser. So this is not something that's particularly new. Over the years, lots of different people have attempted to bring Python to the web browser. So a number of projects include Sculpt, PyPy.js, Brython, and Transcript. And of these techniques that have already been applied, they generally fall into two different categories. So the most common one is transpilation. So the user's program is submitted to a transpiler that takes Python code and spits out JavaScript ahead of time. And some of these techniques are more advanced, and they can do this sort of at runtime. You can give the transpiler runtime some Python code whilst your application is executing, and it can also then online give you more JavaScript. But that's sort of one class of approaches. Now, the other class of approaches are interpreters, and this is where the user program is interpreted by a JavaScript-based Python virtual machine. So this virtual machine effectively replaces CPython or PyPy, IronPython, any of the existing Python runtimes. And so it actually takes Python source code, it will probably compile it to some bytecode, and then it'll execute that. But the execution engine is in JavaScript. And although there are a world of differences between the two, at sort of the core, interpreted implementations of Python tend to be more robust than transpiled versions, in the sense that it is a much easier surface to work on if you implement the VM rather than having to sort of handle every quirk and construct of Python by transpilation. So I thought I'd briefly touch on how these different things might look. So Brython is an example of a transpiler. And if you look at this example test program, it's a simple for loop from 1 to 10. And when you transpile it, this is what Brython gives you. So it's a very lengthy program, but also this is not everything. So you'll notice there are some variables here that aren't defined. You won't be able to read as quickly as I can tell you this, but there are things like this __ Brython. These are things that there is a JavaScript runtime required to provide. So because most programs will have lots of things that they will all reuse from the core CPython or core Python interpreter, Brython defines a lot of this stuff up front so that programs can leverage these. And also a lot of this keeps track of the program state. So you don't get a free lunch. You can just generate a simple program that itself is very readable. As you would expect, transpiled programs are fairly non-readable. So PyPy.js is an example of an interpreter that's been compiled to the web. And it's very interesting because PyPy.js is actually an interpreted subset of Python. So it's PyPy is based in a special language called RPython, which is a subset of Python. That's compiled to a very strict subset of JavaScript called ASM.js. Which can then be optimized by the browser. So you can read more about ASM.js on Wikipedia, but what's interesting about it is that the idea is a single browser vendor in the past introduced this idea of a subset of JavaScript that could be optimized by the JavaScript interpreting or JIT compilers. And the other browser vendors effectively sort of fell in line. And so although you're emitting JavaScript, because its performance characteristics are more well pinned down, it can run somewhat close to native speeds. So here's an example of some ASM.js. It's an implementation of a function, and it has this annotation at the start saying use ASM, and everything after that is just JavaScript. But when the browser sees this, it can start to apply these sort of performance-facing optimizations. So this is two examples of transpiling and a virtual machine. All of them involve running arbitrary Python code in the browser. But for us in HEP, this is not the end of the story. Most of the HEP ecosystem that we've already looked at today, for example, uses Python extension modules. So NumPy, SciPy, Awkward Array, Boost Histogram, just to name a few. And the question that comes to mind is how can you run those on the web? These things are not written in Python entirely. And so that proposes a challenge to the techniques that I've just talked about. So enter Emscripten. I don't apologize for using any memes, but please don't tell me if I've got terrible taste. Emscripten is really interesting. It's a complete compiler toolchain, and it's implemented in LLVM. And the idea is you can give it programs in C++ and in C, and it can spit out something that can be run in the browser, which means JavaScript, ASM.js. So for example, here's a really trivial Hello World program. It just includes some standard IO. It has some printf. This is the kind of thing that would be really easy to compile with Emscripten. And through the Emscripten command line tools, you can compile and then link, much in the same way you would a conventional C or C++ program, to build a web page, in this case test.html. So the MCC tools are how Emscripten is used, and when you go through the link stage, you effectively describe what kind of target you build. Do you build a web page that has a default interpreter that you can REPL that you can work with, or do you build a module that can be linked into, so included in some other code that you've compiled already? So this is the crux at which this talk is based. And the question that comes to mind next is, where do you go from here? So being able to just run some arbitrary code on the web isn't enough. So if you were writing an application that's being deployed on a web page, perhaps. But for us, modern software, it has the 3 C's. It's composable, it's collaborative, and it's complicated, it's complex. And so we need a lot more than just the ability to compile some code to the web in order to move forward from here and actually have a platform. I would say we need to build a software ecosystem. So this is where we bring in Pyodide. And Pyodide is fundamentally a project that leverages Emscripten, but it facilitates interfacing between JavaScript and Python using a foreign function interface. So this means that if you want to interact in the JavaScript realm from Python, you can do that, and vice versa. So for example, here is a small snippet that in Python creates a callback that should be triggered when the user clicks on the body of the DOM. And upon doing that, it invokes this callback using the foreign function interface that Emscripten provides through Pyodide. Well, Pyodide provides leveraging some tools from Emscripten. And it also has features that enable you to install packages from pip, so using like pip from PyPI, the Python package index. So here's an example of how you would do that. You'd import the micropip module. You'd install, for example, matplotlib. This happens asynchronously because it has to perform some network I/O, and so this blocks the top-level program using Python's built-in async await functionality. And then finally, you can import matplotlib, and that's how you would get packages at runtime. So this means that you get all of the pure Python, which means no compiled code, wheels from PyPI, and there is sufficient metadata to tell us that we can do that. And it also means that you get over 200 other compiled packages where those packages have been specifically compiled for Pyodide. And so it's worth then taking note of how Pyodide fits into this whole sort of development ecosystem. You might have heard of something called PyScript. PyScript is a new project that leverages an old project, that is, it's built upon Pyodide, and it's sort of designed for people who are writing, I guess, web pages first. The idea is you write an HTML document, you embed PyScript, and then you get this sort of functionality from Pyodide for free. If you wanted to add a package to Pyodide, I've just mentioned there are over 200 of these in their repo. What it involves is creating a recipe in the Pyodide repository. So this is a recipe. It looks very similar to the conda-forge, the conda build recipes that some of the people here might be familiar with. And it is indeed very similar, but there are some differences that mean it's not a direct conversion, not least because you have to strip out anything that doesn't really make sense when talking about the web. One of the things in particular is to get rid of the annotations to conda recipes that are used for sort of doing cross-platform compilation and things like that. Don't ask me for an exhausted list. I can't remember off the top of my head, but it is on Google. And so it's worth taking note of that if you do want to build a recipe for Pyodide. So this is the awkward CPP recipe. It downloads our wheel. It doesn't do anything differently to it. It just tells it that when it builds it, we want awkward's compiling machinery to know that we're in Emscripten. And that just means we can turn off some things that don't work out of the box on the web. So Pyodide is fantastic, but there are some challenges with using Pyodide. So it has one of the big limitations being that you can't pre-install a Python package like you would in a normal Python environment without actually rebuilding the entire Pyodide distribution, which is a sort of big blob. Which means that as a developer, it's quite painful to sort of iterate on things for Pyodide. But it also means as a user, if you want to build an experience in which you don't have to recompile the entire Pyodide distribution, you end up having to install things at runtime, which is why if you go to a lot of websites that are using Pyodide, like Awkward Array's Try It page, for example, we have an install step in the very first line, which is a little bit ugly, but somewhat unavoidable. Packages in Pyodide are built as a distribution. They're all built together, and it means that when they make a release, you have no control over which versions you choose. You can only get the versions that are available in that release. And that has some particular challenges for things like reproducibility. It means that if you want to deploy something to the web and say, this is what it was, you can't easily say, these are the exact versions that were used here. You have to go and do some additional lookups. Furthermore, it means that if you have incompatibilities between different versions of packages, you're sort of stuffed. And so those are sort of the challenges that come from this distribution model. Another thing about Pyodide as a developer that's not super fantastic is that it uses a custom set of tooling to build releases. There's already a whole plethora of build tools around in the ecosystem, including for conda-forge, but Pyodide builds their own. They're still using a lot of the Python build tools, but they have layers on top of that. And that means they're a source for bugs, which I'm sure all of us would have encountered if they've played with this before. But it also means that there is a lot less knowledge transfer between things that people might already know and Pyodide itself. So if Pyodide is sort of the unhappy Winnie the Pooh, then Emscripten Forge is sort of the holy grail here, in my view. This is a very technical graphic, but Emscripten Forge is a community-maintained distribution. If you've heard of conda-forge, it's exactly the same thing. This means it crowdsources the maintainership of the recipes that go into the Emscripten Forge distribution through this kind of centralized model of there being a central repository that people have to gain access to. It leverages all of the existing tooling around Conda and Mamba, subject to some constraints. So although it is the same tooling, it is slightly different in that it's a new set of tools are being built for Conda and Mamba, and it uses those, not the default ones. So here's an example recipe for a demo, not for this talk, but for a demo that this talk will give. And you can see that the only real thing that of note here is that it includes the Emscripten Forge channel as well as conda-forge, but everything else under here looks like normal package names that you're familiar with. It supports pinning package versions, as you can see here, which is really good for reproducibility. It also means that we can pre-install packages because Emscripten Forge provides this ability through their tooling to sort of build everything into these single artifacts from these disparate packages. And it also has features to enable you to prune the contents of packages that you're including so that if they include large test suites, you don't have to launch those onto the web for your application. All of this stuff is built on ASM.js. But ASM.js is not where the story stops for compiling things for the web. I like to think that software engineers had decided that things were just too simple with ASM.js and they needed to make things even more complicated. So they came up with their own stack-based virtual machine, which executes a new bytecode format, although not so new these days, called WebAssembly. And Emscripten is interesting as a tool because it can compile C++ programs, not just to ASM.js, but also to WebAssembly through another tool called binary N that we don't need to worry about. So this kind of blows my mind. There's so many things going on here, but I think what's interesting here is that WebAssembly provides a much better target for the web. It's a well-defined subset that browser vendors can agree on. It's smaller in terms of binary size, meaning that you can get better throughput in your execution engines, but also it takes up a lot less space on the network, which is great for loading your applications. You can also build up a whole load of dedicated tools for this stuff. There's a lot more to say about it, but it's not the focus of this talk, so I'm just going to leave it there, that WebAssembly WASM is kind of the final goal of this, this roadmap. Now, the point of this talk is talking about analysis. Running Python code in the web pages is cool, but most of us here aren't application authors. We either write frameworks like PyHF and things like that, or we're writing analyses themselves and doing physics. So a lot of us will probably be using the JupyterLab or Jupyter Notebook. And these days, I would just make a very quick side point. If anyone is still using Jupyter Notebook and they've not tried JupyterLab, I encourage you to try it. And if you're using the old Jupyter Notebook, which is Jupyter Notebook 6, take note that there is now a Jupyter Notebook 7 that will be updated in future because it's based upon JupyterLab, but it looks like a Jupyter Notebook. So yeah, that was just a quick aside. This talk itself is actually written in JupyterLab as an aside point. So it's just this tool, an extension called JupyterLab Deck. And I think it's fantastic. But moving on, JupyterLab. This talk was originally in dark mode, which is why I can't see the logo. But it's built in TypeScript, which just transpiles down to JavaScript. It's composed from the ground up of these plugins that do everything from the core functionality like editors all the way up to providing the extension that implements this slideshow. It's interesting because it can communicate with remote servers to execute code, to browse files, and so on. But at the moment, JupyterLab requires someone to run a web server to serve the application itself, but also to perform the file I/O and to execute your code in kernels. Now, if you want to give an anonymous user the ability to run your demo, you don't want them to have to download all your dependencies and run them, which is why we have Binder. And obviously, everyone at this conference will have heard Binder already. It's a tool to give you a notebook session in the browser, effectively. And Binder is great. mybinder.org is free. And it's brilliant, not just for this reproducibility thing, for live demonstrations, but also because it provides a mechanism by which we can describe reproducibility of our artifacts, something we can have a hope of running in future. The challenges with Binder, in particular with mybinder.org, which is this public-facing endpoint, is that it has limited resources. Google recently pulled funding, and I have mentioned this before, but it is quite important, from the Kubernetes provision, which means that a lot of people are running into either being unable to run things on Binder or finding intermittent problems with it. So it is something that we take note of as a community where we are trying to share resources with one another. A new project in this space that I think has some merit, not just from well, I'll get into it and then we can just talk about the merits, I suppose. JupyterLite. So JupyterLite is JupyterLab. The only difference is that anything that requires a Python or otherwise web server to run on someone's computer has been lifted up into the browser. So it all runs entirely client-side, but with the option to talk to remote servers where necessary. So it reuses most of JupyterLab's extensions. As I mentioned, JupyterLab has this extension model, but it has some additional things for the in-browser stuff, so particularly for kernels. And because it's based on JupyterLab, it supports real-time collaboration. Multiple people can open a Jupyter Notebook or JupyterLab session in different parts of the world and collaborate on things. It has file browsers, everything you would expect. And in order to facilitate code execution, it has these kernels being Jupyter's sort of description of processes that run code and provide results to some caller. The kernels for the web are often Pyodide based. And so we've already talked about Pyodide. The Pyodide kernel for JupyterLite that enables you to run in the browser is called JupyterLite Pyodide kernel. It provides an interesting magic called piplite, which effectively allows you to install wheels in a sort of very convenient way inside of a notebook. And so here's an example of how you'd install awkward array in your browser in a Jupyter Notebook running in JupyterLite. There is another kernel called Zeus Python. And in practice, this is a re-implementation of the IPy kernel. It's written in C++, and it's provided by the QuantStack team, if I remember correctly. In practice, I found it to be a lot faster than IPy kernel, both in starting up and in executing. It supports nearly all of the same features that IPy kernel does. And it has a really interesting side effect, which is that it supports this idea of bundling different packages together into a single environment from a conda environment definition. So if you remember in program 9 earlier, we talked about this conda environment for a demo. This could be compiled by JupyterLite to be provided as a single runtime environment for JupyterLite. So it means you don't have to have install steps in your notebooks, and it means everything sort of just works. There are some challenges with this. If I might need to zoom out, actually, that's an interesting. There we go. There are some challenges. They're all very exciting, but here are those challenges. Number one, Emscripten doesn't really support certain kinds of things. It provides a POSIX abstraction, but things like sockets are fairly limited. Threads are not well supported at the moment. File system access is a bit finicky. It has to be done through a service worker. And starting a kernel can take some time. For the demo that I was going to show, it'll take about 10 seconds. And finally, CORS. CORS is the really big thing. CORS is a security model by browsers that effectively is designed to stop rogue JavaScript stealing your credentials by making requests you don't know about. But it has the side effect that if you want to make web requests in your JavaScript applications, sometimes they'll be blocked for reasons that you don't necessarily realize. And so these are all things we have to think about and contend with in this space. I'm going to skip over that for now because I've got a very short demo to show and I don't want to be too pushed for time, but I'd be happy to sort of touch on this later. So there is a demo. I'm not going to click that link because I've already pre-warmed this demo. So this is Jim Pawlowski's talk from last year's HEP. I have slightly tweaked the tutorial, which was a bit naughty of me actually, but just to update it to the latest version of these packages. I did that in order to run this on CPython, not just in the web. So this tutorial, I'm going to zoom out. You don't need to be able to see everything, but if I run the first couple of cells, it'll give all of the names of the package versions. And you can see up here that the kernel is doing things. Now, it's slower than if it runs on your host machine. That's because it's actually performing some I/O, well, some network stuff. And you can see that I've got some fairly latest versions of these packages. What I'm going to do now to save time is I'm going to run everything just below this, and we're going to scroll down and go on journey. If I haven't made a mistake, I've made a mistake. Let me try that again. Wait for the kernel to restart. Kernel's restarted, I believe. This gives me so much confidence, though, that you can never trust a web demo unless it doesn't actually work first time. Okay, I'm going to reload the page just because I think it's being slightly fiddly. And this is a really good time to point out some of these things are in their teething stages. So you will run into things like I've just experienced where things don't seem to behave properly. So I'm going to import NumPy again, and let's see what happens. Okay, NumPy has imported this time. Import the other packages. All right, everyone hold your breath. Okay, that cell worked. Great, things are back on track. So you can see that everything in this demo you would expect to see. We're seeing histograms. Jim did all of this work, I believe. So I won't go into, you can see this tutorial again from 2022. What gets interesting is we come down and use uproot, right? So now we can open a root file that you can actually see in our data section here. The root file has all of the normal features that a root file should have, and uproot can read them. So we can go all the way down, loading in some awkward arrays. And if we go all the way down, we'll catch up with the execution because we're quite fast. These have all been run in this session. This is an expected error where you're doing something wrong. And finally, we should get down to a couple of histograms of Z-peaks. Okay, there is the demo. The point of this demo is not to show you how to write something for the web. I didn't have enough time to cover everything from how you'd author a package to how you'd use a package. The takeaways from this talk that I wanted to leave people with is that A, you can deploy to the web Python packages, even in our ecosystem, that have a huge number of compiled components. B, you probably should think about it. Taking the strain off my binder is a really good motivation, but I don't think it's the only motivation. I think being able to archive things and talk about the web itself is such a slow-moving baseline in terms of the stability it provides. There's a lot of stuff happening in JavaScript land that's crazy, but ultimately, if you open a web page up from 10 years ago, it still runs. And the same is true of most things with the web. The backwards compatibility is taken very seriously. So there's a really strong impetus for us to provide things in some kind of web form, I think, because of the fact that they will last a lot longer, perhaps, than some of the other binary, other tools that we work on. Secondly, WASM WebAssembly works anywhere you have a WASM interpreter and you provide the correct runtime, unlike the other architectures, which are specialized per architecture and so on. And I think finally, it just makes it easier for users if it works, that they just click on a web page and it loads. And I'm confident that all this stuff will get faster and be more stable in future. So hopefully the takeaway from this talk is maybe think about this in future if you haven't yet. And please report errors when things don't work. I've tried to port iMinui recently. I ran into a runtime error, which I need to fix, but it is doable. We ported, we got uproot to work, which is quite easy. We got awkward to compile. and Matplotlib was already there, and so was NumPy. So it is doable. And if anyone wants to talk about how to create those recipes, feel free to open a dialogue with me. You can find me on GitHub or probably in the description of my profile on Indico. Okay, I think it's a good time to yield back if anyone has any questions.
Great, yeah, thanks a lot. I really like your last argument about the hope that it might be nicely conserved due to the backwards compatibility. So I see there's a raised hand from Matthew.
Yeah, Angus, thanks for the fantastic talk as always. This was super fun to see. So if I can continue riffing off of the point that Nikolai just made, yeah, I think that was a fantastic ending, but I guess a question along with that, you had shown, let me scroll through, yeah, you had shown that in program 9, you had said like, okay, this is the conda environment for this talk's demo. And you had also mentioned that it supports package, the ability to like pin packages, and I agree that's good, but specifically around this area of being able to try and run things into the arbitrary future.
Yes.
Even if we pin the top level dependencies, then I think people have gotten to the situation where you're like, oh, but now my dependency shifted underneath, and that's one of the, and then you run into issues, and then and this is one of the reasons that I'm a big proponent of lock files. But so is there lock file technology is usually a very contentious kind of tribal falls into different camps. So can you use something like, since this is kind of like a conda environment, does this mean that you can use conda lock to be able to build a lock file that works with Emscripten forge as well?
Right. Yeah. This is a really interesting space. I actually meant to put this right at the start of the talk, and I completely forgot. I'm not an expert on a lot of this stuff, so take what I do say with a pinch of salt. All of this stuff is being built on a new suite of conda tooling because a lot of people have been unhappy with the conda tooling, and that's where Mamba and Micromember have come from. There's now this thing called prefix.dev, which is another initiative providing the Pixie manager that's kind of like poetry for conda. And there's also a whole load of other stuff that's happening around, what is it called? It's gone from my brain. There's about 2 or 3 kind of versions of conda build tools around, and they are progressing towards these newer tools like Micromember. The Micromember is not the only, on the build side, there's also something called Rattler, which is by the prefix.dev team. And the point of this little weird contextual point is that I think the old conda lock format's considered to have quite a few shortcomings, and there are plans, although whether there's actually mobility behind those, to move towards a new lock file format that I assume Micromember would support and Mamba would support. And if that's the case, I can naturally see that lending over very trivially to the JupyterLite stuff. It is a lot of the same stuff under the hood. So it's just a case of implementing the user interfaces for that, although I suspect that the actual lock file itself will need to be redefined in order to do that. And I agree with your premise. You do want to lock everything. In terms of reproducibility, one interesting thing is that producing a sort of static web page is very much like producing a Docker image, and that you don't have to worry about this pinning problem from that perspective because it's already been compiled, although it means that someone else can't just download your environment and get started, which is obviously why pinning is important in the first place. So roundabout answer is yes, locking is important. It should come into the picture. I don't think it's in the picture right now. This is quite new stuff, I think.
Okay, fantastic. Yeah, super appreciate that. And while you very humbly mentioned that you're not an expert in things, it's fantastic to still have people like you who are pushing forward on this to inform the rest of us who are definitely not experts.
That was been super interesting. Thank you for having me, everyone. Is that the kind of probably the end of the questions, I'm guessing now? I kind of ran over a little bit.